In this video, we're going to talk about waves and characteristic of waves like frequency, wavelength, energy, amplitude, speed, period, things like that. So let's say if you have a graph, and on this graph, you have a sine wave. Let's say this value is 5, and this is -5, and this point is about 10 meters. So what is the amplitude and the wavelength of this wave if you're given this information? The amplitude of the wave is simply the height between the center and the peak. The peak is called the trough. This is known as the crest. So as you can see, the amplitude is 5. Another way you can calculate the amplitude is you can subtract these two numbers and then divide by 2. So it's the top number minus the bottom number divided by 2. So that's going to be 10 divided by 2, and you're going to get 5. That's another way in which you can calculate the amplitude of a sine wave. Now what about the wavelength? The wavelength is the length of one cycle. So let me highlight what a cycle is. So the wave has to go up, then it goes back to the middle, and then it has to make the trip all the way down, and then return back to where it started. That is one cycle. The length of that cycle is 5 meters. Notice that 2 cycles is 10 meters. The second cycle is right here. So the wavelength, which is typically represented by the symbol lambda, the wavelength in this example is 5 meters. Let's try another example. So let's say if we have a wave that looks like this. And at this point, let's say it's 28 meters. And the trough is located at a value of 8. And let's say the crest is located at a value of -2. What is the amplitude and what is the wavelength? What I would do is draw the center point of the graph. Notice that it's been shifted up. The question is, how many units has it been shifted up the y-axis? To find that value, it's simply the midpoint between the highest value and the lowest value. To calculate it, we need to take the average of -2 and 8. The average is the sum divided by 2. That's going to give us the midpoint. -2 plus 8 is the same as 8 minus 2, which is 6. 6 divided by 2 is 3. So 3 is right between 8 and -2. So we can see what the amplitude is. The amplitude is the distance or the difference between the trough and the midpoint or the center line. So 8 minus 3, that's a value of 5. Also, you can also calculate it by subtracting 3 minus -2, which is also a value of 5. Or you could use that other equation that I showed you earlier. The amplitude is the difference between the highest point and the lowest point divided by 2. So 8 minus -2 divided by 2. 8 minus -2 is the same as 8 plus 2, which is 10, and 10 divided by 2 is 5. So there's a lot of different ways in which you can calculate the amplitude of a wave. Now what about the wavelength? How long is it in this particular example? So let's count how many cycles that we have. We need to find the length of one cycle. So the wavelength is basically the distance in meters divided by the number of cycles. our goal is to find the distance of one cycle. So we need to find the ratio between distance and cycles. So this is the first cycle, that's 1. Here's the second cycle, that's 2. Here's the third cycle, that's 3. And we have a half of a cycle, so we have a total of 3.5 cycles. So it's 28 divided by 3.5. Let's multiply top and bottom by 2 so we can get rid of the decimal. 28 times 2 is 56. 3.5 times 2 is 7. How many times does 7 go into 56? 56 divided by 7 is 8. So that's the length of one cycle, which is defined as the wavelength. So the wavelength is 8 meters. This position is 16 meters. And at this point it's 24. And then we have half a cycle, which is 4, which lends us to, or leaves us at 28. So now you know how to calculate the wavelength from a graph. So now what about the relationship between frequency and period? The period is the time it takes for the wave to complete one cycle. So the period is the time divided by the number of cycles. Frequency is the inverse of a period. Frequency is the number of cycles that the wave makes in a single second. So frequency is the number of cycles divided by the time. The number of cycles doesn't really have a unit. So for period, it's time over cycles, so the unit for period is like seconds. The period is the type of time. It's the time it takes to make one cycle, so it's measured in seconds. Frequency is the inverse, not the inverse, but the reciprocal of the period. So frequency is 1 over p. Now in some textbooks, the period is represented by capital T. So this is the same as 1 over t. You've probably seen this equation, F equals 1 over t somewhere. So that just tells you frequency and period are inversely related. So the unit for frequency is 1 over seconds. Or you can simply view it as s to the minus 1, which is the same as the unit hertz. So that's the unit for frequency. So make sure that you know this equation. Frequency is 1 over period. And if you want to find the period from a graph, use this equation. It's the time divided by the number of cycles. And if you want to find the frequency from a graph, it's the number of cycles divided by the time. Consider this example. So let's say instead of having meters on the x-axis, we have the unit time. So let's say it's 8 seconds at that point. What is the period of this wave? So our goal is to find the time it takes to complete a single cycle. We need to find the time it takes to get to that point from the origin. So let's count the number of cycles. So that's the first cycle. This is the second cycle, and this is the third cycle, and here's the fourth cycle. So there's 4 cycles. The period, which I'm going to use as capital T, is the time divided by the number of cycles. So in 4 cycles, we have a time of 8 seconds. So therefore, it's 2 seconds per cycle. Now that's the period. So at this point here, this correlates to 2 seconds. The second cycle ends at 4 seconds. The third one ends at 6. And the last one ends at 8. So the period is 2 cycles per second. Now what about the frequency? So the frequency is 1 over period. So the frequency is 1 over 2, which is 0.5. The frequency is the number of cycles that occurs in a single second. So if the frequency is 0.5, that means that there's 0.5 cycles in 1 second. Now let's make sense of it. 1 second occurs here, and at this point we only completed half of a cycle. So that's the frequency. We've completed half a cycle in 1 second. The frequency is the number of cycles in 1 second. So 0.5 cycles corresponds to 1 second. That's the frequency. So you can say it's 0.5 hertz. Let's try another example. Now let's say if this point represents 0.25 seconds. What is the frequency and what is the period? So notice that we have the time it takes to complete 1 cycle. That's the period. So therefore the period is 0.25 seconds. Now to calculate the frequency, it's 1 over the period. So 1 divided by 0.25 gives you 4, or 4 hertz, which is 4 cycles per second. Notice that this is 0.5, this is 0.75, and this is 1. So notice the number of cycles that we complete in 1 second. This is 1 cycle. Here's the second cycle. This is the third cycle. And this is the fourth cycle. So there are 4 cycles that occurs in a single second. And that's the frequency, the number of cycles that occurs in 1 second. So that's why the frequency is 4 hertz. In 1 second, there are 4 cycles. So you can use the equation to calculate all of the answers. We said the period is the time divided by the number of cycles. So if you take a time of 1 second and divide it by the 4 cycles that corresponds to it, you're going to get the period, which is 1 over 4. 1 over 4 is 0.25. Now to calculate the frequency, it's the number of cycles divided by the time. So in this example, there are 4 cycles that occurs in a single second. So 4 over 1 gives you a frequency of 4 hertz. So there's many ways in which you can calculate the period or the frequency. If you could find one, then you could find the other. You just got to find out which way is easier. Now let's try one last example with graphs. So let's say if you have a wave that looks like this. And at this point, you know that the time is 14 seconds. How can you figure out the time at this point, which is the time for 1 cycle? So we know that's the period. How can you find the period of this particular graph? Feel free to pause the video and try this example. So notice that we can break this wave into 7 segments. 1, 2, 3, 4, 5, 6, 7. So the length of each segment is 14 divided by 7, so it's 2 seconds. So this therefore is 2, 4, 6, 8, 10, 12, 14. And the length of 1 cycle, we can see, is 8 seconds, so that's the period. So that's a technique that you can use to find the period of a wave if you're given a value that doesn't end at a complete cycle. In such a situation, it helps to break each cycle into 4 equal parts. Now let's go over some other equations that you need to know. You need to know the relationship between wavelength and frequency. As the wavelength increases, which is represented by this lambda symbol, the frequency, which is v, or you can write f if you want, the frequency decreases. The wavelength and the frequency are inversely related. Now we know that the frequency is inversely related to the period. So as the wavelength goes up, the period goes up. the wavelength is inversely related to the energy. As the wavelength goes up, the energy goes down. So wavelength and period are directly related, and the frequency and the energy are directly related. The equation that relates wavelength and frequency is this one. C is equal to lambda times V, or we'll just use lambda times F. F is for frequency. C is the speed of light. This is how fast light travels in a vacuum or empty space. So the speed of light is 3 times 10 to the 8 meters per second, and that's very fast. That means in 1 second, light can travel a distance of 300 million meters. Now let's say if you have a wavelength of 600 nanometers. How can you use this information to calculate the frequency of this wavelength? Frequency is the speed of light divided by wavelength. So it's going to be 3 times 10 to the 8 meters per second divided by, we don't want to put 600 nanometers because nanometers and meters, they don't match. We need to convert the nanometers into meters. It turns out that 1 nanometer is equal to 1 times 10 to the minus 9 meters. So 600 nanometers is simply 600 times 10 to the negative 9 meters. So we can see that the unit meters will cancel, and you're going to get the unit 1 over s, 1 over seconds, which is frequency, which is the same as hertz. So let's type it in. 3 times 10 to the 8 divided by 600 times 10 to the negative 9 gives you a frequency of 5 times 10 to the 14 hertz. Now once you have the frequency of a photon of light, you can calculate the energy of that photon. Using this equation, the energy is equal to Planck's constant times frequency. Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. So let's pay attention to the units. Frequency, which is in hertz, we can also represent it as 1 over seconds. So notice that the unit seconds cancel, which means that in this equation the energy of the photon is in joules. So if we multiply those two numbers, this is going to give us an energy value of 3.313 times 10 to the negative 19 joules. Now sometimes you may need to convert it to electron volts. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So to convert it, we need to divide by 1.602 times 10 to the negative 19 joules. As you can see, the unit joules will cancel if we set it up this way. Notice that the 10 to the negative 19 value will cancel as well. So all we need to do is type in 3.313 divided by 1.602, and that's going to give us the energy in electron volts. So it's going to be 2.07 electron volts. So far, we've considered how to calculate the frequency of a photon in pure empty space, in a vacuum, and also the energy under those conditions. But let's say if light is passing through water or glass or diamond, what's going to change? Whenever light passes through a material, it slows down. The speed changes, and also the wavelength changes with it, but not the frequency. The frequency remains the same. There's an equation that helps you to calculate the speed of light in a different material. Here's the equation. V, not the frequency V, but velocity. V is the speed of light in a vacuum divided by the index of refraction. So C is still 3 times 10 to the 8. This is the speed of light in a vacuum. n is the index of refraction. So let's use water as our example. The index of refraction for water is about 1.33. Now v represents the speed of light in this material, in this case, the speed of light in water. We can use this equation to calculate the speed of light in glass or the speed of light in diamond. As the index of refraction increases, the speed of light in that material decreases. The index of refraction for glass is about 1.5. For diamond, I believe is about 2.4. So light travels much slower in diamond than it does in glass. And light travels slower in glass than it does in water. But in pure empty space, light travels at its maximum speed of 3 times 10 to the 8 meters per second. So let's calculate the speed in water. So all you have to do is divide 3 by 1.33. And you should get 2.26. And then you can simply add this value times 10 to the 8 meters per second. So as you can see, light is a little bit slower in water than it is in pure empty space. Now what about the wavelength? We see that as the index of refraction decreases, the speed of light decreases. But what about the wavelength? What effect does it have on it? As the index of refraction increases, it turns out that the wavelength decreases as well. The equation that you need is the wavelength in a material with an index of refraction of n is equal to the wavelength in empty space divided by n. So this time, let's choose the same wavelength that we had in the last example. That is 600 nanometers. So it's going to be 600 nanometers divided by the index of refraction for water, which is 1.33. And so we're going to get a wavelength of approximately 451.1 nanometers. So that's the wavelength of light in water. So as you can see, the wavelength in empty space was originally 600, but now in water it decreased to 451.1. And the speed is now 2.26 times 10 to the 8. So what we're going to do is calculate the frequency. So using this equation, we know that the speed of light is the wavelength times frequency. Now we have to use not the speed of light or in a vacuum, we have to use the speed of light in water, which is v, and we have to use the wavelength in water, which is lambda n times frequency. So the frequency is going to be v divided by lambda. So the speed of light in water is 2.26 times 10 to the 8 meters per second, and the wavelength of light in water in this example is 451.1 times 10 to the negative 9 meters. So if we divide those two numbers, we're going to get 5.01 times 10 to the 14 hertz. Now granted, these answers are rounded, so that's where the 0.01 comes from. But if we didn't round it, we would get exactly 5 times 10 to the 14 hertz, which is what we had in the previous example. So notice that the frequency, it doesn't change if light is in empty space or if it's in water. So as light passes from one material to another, the speed of light will change and the wavelength will change, but the frequency remains the same. And because the frequency is the same, the energy is going to be the same as well, because the energy is proportional to the frequency. So we're going to get the same answer as we did in the last example. So here's a question for you. Let's say if you have two materials, Let's say this is diamond and this is glass. As light passes through diamond to glass, what's going to happen to the speed of light? Will it increase or decrease as it travels from diamond to glass? Think about it. Now we know what happens as light travels from empty space to water. So let's say if we have a container with water. As light travels from air to water, it's going to bend. This is known as refraction. And as it passes from air to water, will the speed increase or decrease? So you have to think about what's happening to the index of refraction, or how it's changing. The index of refraction of air is 1, and for water is 1.33. So the index of refraction increases in this particular example. As the index of refraction increases, the speed of light decreases. Light travels slower in water than it does in air because water has a higher index of refraction. And also, the wavelength will decrease as it goes from air to water. The frequency is going to stay the same, and the energy of the photon will be the same as well. Now, from diamond to glass, the reverse is true. The diamond has an index of refraction of 2.4, and for glass is 1.5. So we're going from a material that has a high index of refraction to a material that has a low index of refraction. Therefore, N is decreasing. And whenever the index of refraction decreases, the speed of light will increase and the wavelength will increase as well, as light travels from diamond to glass. Now, the next thing that you need to be familiar with is the electromagnetic spectrum. We're going to rank it from long wavelength to short wavelength, or from low energy to high energy. So the first one in the list are radio waves. Radio waves have the lowest energy, the lowest frequency, but the longest wavelengths. After radio waves, you have microwaves, and then after microwaves there's infrared, and then after that you have visible light, RGB, red, orange, yellow, green, blue, there's indigo, and then there's violet. After violet, you have ultraviolet radiation, and then X-rays, and then gamma rays, and after that, you have cosmic radiation, which I'll just write C for cosmic radiation. So as you go to the right in the electromagnetic spectrum, the frequency increases. So gamma radiation has a higher frequency than X-rays. And also the energy increases. Frequency and energy are directly related. So X-rays has a lot more energy than UV rays. Now on the left, the wavelength increases. Radio waves, they have the lowest energy, but they have the longest wavelength. So which one has a higher frequency? Microwaves or ultraviolet light? So frequency increases to the right. Ultraviolet light has a higher frequency. Now which one has more energy? Blue light or red light? Energy increases to the right, so since blue is to the right of red, blue has more energy. Now which one has a longer wavelength? X-rays or gamma rays? Wavelength increases to the left, so X-rays, which is to the left of gamma rays, X-rays have a longer wavelength. Now which one has a lower frequency? Infrared radiation or red light? If frequency increases to the right, the one that's to the left has the lower frequency, so that's infrared radiation. Now which one has less energy? Microwaves or green light? So energy decreases to the left, so microwaves have less energy than green light. And which one has a shorter wavelength? Infrared or ultraviolet radiation? The shorter wavelength is the one that's on the right side, so ultraviolet radiation has a shorter wavelength. Now the next thing you need to know is the range of the visible light spectrum. Red light is around 700 nanometers in wavelength, and violet light is about 400 nanometers. So at this point, it's 700 nanometers, and over here, it's 400. Violet light is about between 400 and 450. Blue light, it ranges about 450 to 500. And green light is 500 to 570 nanometers. Yellow light has a smaller range, it's like 570 to 590. Orange is about 590 to 620. And red light has the longest range, it's 620 to 700. So now you know the visible light spectrum and the wavelengths that corresponds to each color. So that is it for this video. Thanks for watching and have a great day.